Today's lesson is on fluid pressure. This is topic 7 in our mix and flow of matter unit. And like I said, we do need to learn another formula for pressure. So when we are talking about pressure, it's a measure of the force acting perpendicular to a unit area. So for example, like leaning against a wall. Pressure is measured in pascals. Force is measured in newtons, and area is measured in meters squared. So when we have newtons per meter squared, it's also called a pascal. Therefore, pressure is measured in either newtons per meter squared, or you can write it as pascals. Okay, so pascals, this was a French scientist, Blaise Pascal. He worked with pressure, so this unit, newtons per meter squared, is named after that French scientist. All right, also 1 kilopascal, kPa, is equal to 1,000 pascals. All right, so when we were looking at density, we also used this triangle method, and we can use this triangle method again for all of our formulas. So the first one is pressure. Pressure is force divided by area, so you can just cover up the pressure, and we have force divided by area. If you're trying to find force, you will cover up force, and you're left with force is equal to pressure times area. And lastly, if you're trying to find the area, cover up area, and you're left with force divided by the pressure. All right, this is the worksheet that has the formulas in there as well. So the same formulas we just talked about. Pressure, it's the amount of force per unit area. Force divided by area to calculate pressure. Area is force divided by pressure. And lastly, force is pressure times area. Okay, our pressure is expressed in the units newtons per meter squared, which is equal to a pascal. And then a kilopascal can also be used. So let's take a look at our first example where we have calculating the pressure if 32 newtons of force is applied against a surface of 5 meters squared. So if we need to, we can just go back here and get our formula. Pressure is equal to force divided by area. That's what we're trying to calculate. We don't know pressure, so pressure is what we're calculating. All right, so pressure is what we don't know. Force is always measured in newtons. We know the force. It tells us in the question is 32 newtons. And area, we are also given 5 meters squared. All right, so we know our formula is pressure is equal to force divided by area. So therefore, our pressure will equal to 32 newtons divided by 5 meters squared. All right, and now we just have to put that into your calculator. Just 32 divided by 5. Just need to find my calculator. So 32 divided by 5, which gives me 6.4. All right, and notice here our units are newtons per meter squared, but we know newtons per meter squared is equal to pascals. So therefore, we just say 6.4 pascals. All right, so our next question, calculate the force applied if the pressure is 9.2 pascals and the area is 4.9 meters squared. So in this one, we don't know the force. So force is what we don't know. Pressure, we know it is 9.2 pascals. And area we know as well, it is 4.9 meters squared. All right, so let's just go back to figure C what our formula is for force. Force is equal to pressure times area. So pressure times area. All right, so we're going to take our 9.2 pascals and we're multiplying it by 4.9 meters squared. And remember, force, the unit for force is in newtons. All right, so put that into your calculator. 9.2 times 4.9, which gives me 45.08. The force is equal to 45.08, and the units are newtons. So our next example, we're trying to calculate the area. Calculate the area if 15 newtons of force is applied with a pressure of 2 pascals. All right, so area we don't know. Force is 15 newtons. And our pressure is 2 pascals. All right, and we got that right from the question. So we need to figure out the area. So let's just go back to our formulas here. Area is equal to force divided by pressure. Okay, so area is equal to force divided by pressure. So area will be equal to 15 newtons divided by 2 pascals. All right, so 15 divided by 2 will give us our area. So our area is equal to 7.5 meters squared. All right, so next we're going to look at compression of a gas. So for example, landing on the hard ground versus landing onto an air mattress. The air mattress works as a shock absorber. And what's happening is it compresses when you land on it and it's absorbing the force of the fall gradually. So what are the requirements for compression of a gas? The first requirement is the gas must be enclosed with a seal and sturdy walls. The gas particles within will distribute themselves equally throughout the container. Next, there's space between particles. There's so much space between particles that even after being squeezed, they are still far enough apart to still behave as a gas. And thirdly, an external force is applied to the enclosed gas to push those particles closer together. And therefore, gases are compressible because their particles can be squeezed closer together into a smaller volume. Right, so we'll pause here and just watch this video on pressure in gases. All right, so compression of a solid or liquid. So although there is empty space between particles of solids and liquids, the spaces are already almost as small as possible. So when a force is applied to a solid or a liquid, the particles can't move much closer together. So we say they're incompressible. All right, meaning they are incapable of being squeezed into a smaller volume. All right, so gases we saw are compressible and solids and liquids are not. So instead of changing the volume of either the solid or liquid, the applied force just gets passed along from one particle to the next throughout the substance, all right? Kind of like falling dominoes. So that's what's happening in solids and liquids. What are the advantages of compression? So gases, they can exert a force back when they are compressed, like called a counterforce. So for example, it's used to cushion shocks. So in cars, the air in a car tire pushes back against the force exerted by the weight of the car. And this allows the effect of the force to be spread out over the entire tire rather than being transmitted directly to the body of the car and to the passengers inside the car. And then when the force is removed, the air returns to the original volume and the tire will go back to its original shape. Other examples are airbags in vehicles. Lots of running shoes these days, we see they have pockets of compressed air as well. All right, so here, just some more examples. Here we have all-terrain vehicles. They have wide tires and they're kept inflated to a very specific pressure. Here are some running shoes. They contain these pockets of compressed air. That compressed air is said to be much better than just having plain rubber soles in shock absorption and bounce. And then here, an airbag in an automobile. It uses compressed gas to protect the driver in a collision. All right, just gonna pause here. So next we're looking at atmospheric pressure, so pressure in the atmosphere. So air pressure changes with altitude, so like climbing up a mountain. And just like water pressure changes with depth. The density of air pressure, it decreases as you move farther away from sea level. So for example, climbing a mountain. It gets very difficult to breathe at tops of very high mountains because the air contains fewer number of oxygen molecules than at sea level. There's a device called a barometer, which is used to measure air pressure. Balanced and unbalanced forces. So, for example, when you drink out of a juice box, you may have noticed how the box kind of collapses like so. So what's happening is if the inside of a closed container has lower air pressure than the outside air pressure, the walls of the container will buckle inwards. So buckle in because the lower air pressure inside the container, it doesn't balance the higher air pressure that's on the outside of the container. And that's called an unbalanced force. So the example here is drinking juice out of a juice box. The straw makes a pretty tight seal as you drink from the juice box. So as you draw juice up the straw, there's a reduced air pressure inside the box, and therefore the juice box buckles inwards. Okay, the air pressure that's on the outside of the juice box, it's pushing the walls of the box together. Just a did you know fact, bottled pop on store shelves does not look carbonated because it has been bottled under pressure. So when pop is manufactured, carbon dioxide gas is forced to dissolve into the solution, the syrup. Then the bottle cap is secured before that pressure is released. And the strength of both the bottle and the cap prevents the loss of pressure. If you open up the bottle of pop too quickly, the pressure inside the bottle is released suddenly, and then the carbon dioxide escapes rapidly from the solution, and it's formed so that bubbles or the fizz. And if you shake the pop ahead of time, you've probably seen this happen, or if you leave it outside in the sun, that gives the particles more energy, so more carbon dioxide escapes when the pressure is released. Here, looking at air pressure, how it decreases with increasing altitude. So here the pressure is about 57 kilopascals at the top of this mountain. So Earth's atmosphere doesn't have the same number of air particles at sea level as at the halfway or higher mark. The density of the atmosphere decreases as you move farther and farther away from sea level. And like I said, that's why it gets more difficult to breathe at the tops of very high mountains. There's a fewer number of oxygen molecules up at the tops of mountains. All right, and since pressure decreases as the force pushing down on an area decreases, then you would experience less air pressure higher up in the atmosphere. All right, so I'm going to pause here